Hi everyone, this is Anna Bergstrom, and you'll see Matt Ross's face on this is because he's the one who developed the slides and worked out all the practice problems. I'm just reshooting the video to make it a little bit more clean. So with the help of Matt, we are going to just go through and solve some example acid-base problems. So hopefully by the end of this, you will be able to solve for pH given concentrations of strong and weak acids, and understand how equilibrium constants are used in acid-base reactions. So before we dive in, just some quick reminders. So you'll remember from thermo, we have our equilibrium constant, and for a given reaction, say for an example, we have a moles of A substance plus B moles of B substance yields C moles of C substance plus D moles of D substance. So our equilibrium constant for this, again, is our products over our reactants, and the concentration of our products raised to the power of their activity. So in this case, we have C moles of C, so it's C to the C power. Same with D, and then our reactants are in the denominator, and we have A to the A power and B to the B power. So that's just a quick reminder of what equilibrium is and how it works with acids and bases. So if we have a strong acid, you'll remember from the previous video that strong acids donate all of their protons, and similarly strong bases all of their hydroxide ions. Weak acids and weak bases, they either donate or accept protons depending on the pH of the system. So if we have something that already has a very low pH and we add a weak acid to it, it's not really going to donate that many of its protons. For acid-base reactions, we call this equilibrium constant Ka for acids or Kb for bases. So just the equilibrium constant specific to that acid or that base. And the simplified form of the acid-base equation here, we have Ka, so just our equilibrium constant for our acid, and that is the concentration of the conjugate base times the concentration of the hydronium ions. So these are going to be the products that we're going to get out of our reaction, all over the concentration of whatever acid we put into solution. So we're going to start out with a simple example with a strong acid. So here we're just working with hydrochloric acid. So if we put hydrochloric acid in some water, we're going to end up with some hydronium ions and some chloride ions. So if we add, say, 10 to the minus 3 moles per liter of our hydrochloric acid to pure water, what is the pH going to be at equilibrium? So we're going to switch over here and write out the problem. Okay, so we're going to use our handy ice tables that we developed as a tool in thermo. It works here with acid-base problems. You will be happy to know that all of that work wasn't for nothing. So let's start by writing out our equation. So we have hydrochloric acid plus water yields our hydronium ions and our chloride ions. And as a reminder, we added 10 to the negative 3 moles per liter, which is also the molarity, and what is the pH? That's what we're looking for. So again, we're going to use our ice table. This is a very simplified version of it though. So we have an initial concentration of 10 to the minus 3. Again, because we're dealing with pure water, we don't have to worry about it in this situation. And we're saying, for the sake of this, we have 0 moles of hydronium ions and 0 moles of chloride ions, because we added our hydrochloric acid to pure water. So our change, because this is a strong acid, we're assuming that all of our hydrochloric acid is going to dissociate, all of the protons will be donated. So we are losing X moles here and gaining X moles of chloride and hydronium ions. And again, we know at equilibrium all of our hydrochloric acid has dissociated, so that is a 0. And then if we work through this math, 0 plus X is just X, and same thing with the chloride, 0 plus X is X. So we don't even need a Ka here. We can just use this column to figure out our ending concentrations and then our pH. So here we have initially 10 to the minus 3 equals 0 minus X. If we just move, if we just do our math here, we know that X equals 10 to the minus 3. And therefore, our concentration of hydronium ions is 10 to the minus 3. And if you'll remember, our pH is the negative log of the concentration of our hydronium ions. So we just need to take the pH of this concentration here. So the negative log base 10 of 10 to the minus 3. And that's real nice and easy. Our pH is going to be 3. So that is a really nice, simple equation with a strong acid. We don't even have to go into the weeds of using the quadratic equation like we have previously, because we know everything is going to completely dissociate. That hydrochloric acid is going to donate all its protons. Okay, so what if we are working with a weak acid? This might change depending on what the pH is and what our pKa is, and how much concentration, what the concentration of everything is in solution. So we'll use acetic acid as an example. So if we put acetic acid in water, we're going to end up with some, forgot the name of that, doesn't matter, plus hydronium ions. And our pKa here is 4.75, and when we have a P out front, that means we've already taken the negative log of that. So that'll come back into play in a second. And our initial concentration of acetic acid is 10 to the negative 4th. So we're going to use this equilibrium constant here to calculate what our final pH will be once we add this acetic acid to water. So we will switch back over, get a new piece of paper up here. In water. Plus our hydronium ions. And we'll remember here that our pKa is 4.75. And we started out with some amount of acetic acid. So using our ice tables here, we started out with 10 to the minus 4th moles per liter, so molar. We again don't have to worry about our water. We're assuming that the acetic acid was added to pure water, so our initial concentrations of each of these products is 0. Then we're dissociating some amount of our acetic acid into our products, and that is going to be gained as products. So minus X, plus X, and then plus X for the change line. And then at equilibrium, we have this concentration, initial concentration of acetic acid minus X, and then 0 plus X is X, and 0 plus X is X. Okay, so now we can use the definition of Ka to solve for X here. So again, we started with a pKa, which is the negative log, so we just have to take 10 to the minus the pKa value to come up with our Ka value, in which case that is 10 to the negative 4.75, and that equals in the numerator, the concentration of our products raised to their activity, in which case it's 1 for both, so we just have x times x, which is x squared. And then in our denominator, we have the concentration of our reactants at equilibrium, in which case this is just acetic acid. So we have 10 to the minus 4th minus x. So I'm not going to work through the math here. You guys have done plenty of practice problems, learned how to solve the quadratic equation, or at the very least learned how to use Wolfram alpha to give you answers to solve for x in this sort of situation. So in this case, we would have ended up with two x's, one of which would have been negative, and we know that that's not really physically possible. So we have the answer, which is x equals 3.4 times 10 to the negative 5th. So because we know what x is, and we know that in our equilibrium line we have x is the concentration of our hydronium ions in solution, and we wanted to know the pH, all we have to do is take the negative log of that concentration of hydronium ions. So our concentration here is that value, 3.4 times 10 to the negative 5th, and our pH, again, is the negative log of that, which is 3.4 times 10 to the negative 5th. And if we take the negative log, we will find out that our pH is 4.45. So, given different concentrations of other things in solution, or given different concentration of the acetic acid we added, we would have ended up with a different pH depending on what's going on in that particular problem. So those are just some examples using a strong and weak acid. Of course, it works the same with bases, and we can do more practice with that in class.